I'll get started. Title my talk, Control-Oriented Learning for Dynamical Systems. And what this sort of will revolve around is my work at the interplay between learning and control, particularly for robotics. What this sort of motivated by is that if we look at each of these robotic systems on their own, at least from a dynamics perspective, we're pretty good at coming up with some sort of first principles model of each of these systems. Where sort of the complexity arises is where these robots are operating in different domains and under certain conditions like icy roads and contact and under different wind conditions. And these are the things that are difficult to model analytically. And sort of these are the reasons why we sort of turn to data-driven learning, where we can't write down the model by hand, so we look to data and try and figure out a model for the system overall, or at least some addendum to the model, some model we already have. But a lot of the fundamental and sort of naive ways you might think about doing learning from machine learning don't always work very well in practice when you're talking about closed-loop control. So, for example, naive regression, where you just minimize, a two-norm loss, may work well in minimizing one-step open-loop error. But control tasks happen over long time horizons in closed-loop. So regression, what you might find is that regression for the system and then deploying a learned model for the system that was learned with naive regression would diverge over time with compounding errors over multiple time steps during closed-loop control. So what we need to do, at least what I argue in this talk, is that we need to orient the learning problem around what we're ultimately interested in, which is closed-loop control, or the downstream control objective is the terminology that we use. So rather than just the model fitting objective. So the idea, which we sort of call control-oriented learning, is that we should condition the model to perform better and be more adaptable in closed loop in comparison to models that are learned naively to minimize open loop error. So today I'll discuss 3 different lines of work that we've developed, time permitting, to orient learning around closed-loop control. The first one involved translating the concept of stabilizability or controllability into algebraic conditions that we're going to use as a regularizer for closed-loop control performance during offline learning. The second take is a little bit different. It involves structuring our model appropriately offline in a manner that's generally applicable, but it naturally yields a useful closed-loop controller based on LQR. And then the final work I'll talk about is shifting more towards the online setting and specifically using meta-learning to learn a good extension to a nominal model that you specify maybe through first principles and learning an extension to it that we can adapt well online for adaptive control. Okay? So I'll get started with the first project, which was joint work with some folks at Google and MIT. And it's going back to this regression problem. And what we want to do is integrate some notion of stabilizability, or the ability to stabilize the system as a constraint, with the key idea being that what this should do is prune the hypothesis space of functions that we're fitting over, that we're searching over, and finding one that's somehow attuned to closed-loop control. So the key question, so in stabilizability, what I mean by that is there exists a controller that, as a function of my current state, where I am, where I want to be, x star, and ensures that x of t, my current state, goes towards my x star of t over time. That's what I mean by stabilizability in the general sense. Okay? The key thing we need to sort of overcome here is, if we want to try this out, is we have to be able to describe stabilizability algebraically to construct an optimization problem that we can solve to fit a model. So to do this, we turn to something called contraction theory. So if we look at, let's consider control affine dynamics, x dot equals f of x plus b of x times u. And what contraction theory starts off by doing is linearizing the dynamics, but maintaining the dependence on your linearization point. So you look everywhere, state and input-wise, and you look at the local linear dynamics, or the variational dynamics, to be more specific. This is a family of linear systems, and it's an exact description of small variations of your dynamics near your linearization point. And this is a linear system, at least in your variations, delta x and delta u. So what we can do is we can construct this notion of local energy or local distance. And this is a square distance, but it's weighted by a metric called m of x. It's a positive definite function, matrix function. It basically generalizes the notion of distance and allows it to depend on your linearization point. So like I said, we're sort of generalizing the notion of squared distance with some quantity that allows it to depend on where you're linearizing it. And this thing that we're weighting the distance with is what's known as a control contraction metric, or CCM. And the idea is that we have a quadratic notion of energy, and we have a linear system. So anybody who's done any sort of control theory, this should scream out to you, do some sort of linear control design. That's sort of our bread and butter as control theorists, is linear control design with quadratic costs or quadratic energy functions or Lyapunov functions. So the idea is that if we can design a linear controller, a local linear controller, or variational controller that's linear in the variation in x, and design it in such a way that this differential energy is decreasing locally everywhere. Okay? Well, if it's decreasing locally everywhere, and I integrate that differential control, delta U, between 2 points, x and x star, so along shortest paths between x and x star, I back out another control, and through some a lot more math than I intend to get into in this presentation, we can show that by integrating out control for the original system, we can get something that's stabilizing for the original system. And it shows it basically makes x of t go towards x star of t. So the metric m of x, together with this energy decrease condition, which I haven't really put any specifics on yet, together forms a certificate for stabilizability of our system. So we have dynamics, and we've introduced this additional function along with some conditions that need to be satisfied to make the system stabilizable. So without going into any detail really about how this is derived, the idea that there's few things I want to point out is that it depends on the dynamics, which go into now our model fitting objective at the top. And we also have this decrease condition that ends up looking like a matrix inequality that depends on both the dynamics and the inverse metric. Okay? So you've added an extra thing that you're trying to learn, and it acts as a certificate for the stabilizability of the dynamics functions that you're fitting to data. Okay? The key problem still, there's two problems. One is that the constraints are infinite dimensional. Much like a Lyapunov type analysis, you want it to hold for all x. But we can't tractably enforce this as a constraint, unless other than in some certain conditions. So what we do is we sort of relax this and say, sample some x points and turn this into a finite number of constraints. And there's no data associated with these constraints. There's no output or labels for this data. I can sample as many x's in the state space as I want, so I can cover the state space as densely or as sparsely as I want. The only labels that sort of show up are in the actual model fitting objective. So the other problem here is that it's non-convex. You have matrix inequalities at multiples of f and w, but it's biconvex. So what we do to solve this, we linearly parameterize our metric and dynamics and do alternating convex solves until we converge to some local optimum. And so we actually did this on hardware with real data with a quadrotor. And on the left, we've done sort of naive model fitting. And on the right, we've done our approach. And what we find is that the one on the left is not going to do so well. It's going to start oscillating a bit, right here. And then it starts to square out of control and ends up crashing. While this one on the right manages to sort of track the figure eight that we've sort of commanded it to track. And keep in mind, this is sort of a quadrotor model that's sort of learned from scratch. So we're not providing any base model for it. Sort of wanted to just see how well does this method work for learning a model from scratch. Okay. So with that, I'll move into sort of the second project, which sort of takes a different spin on things. And it'll still be an offline model learning. And this was with some folks at MIT. But it sort of takes the approach, instead of trying to come up with an addendum, like an extra function, an extra certificate function, it looks at how do we do control, or how do we build controllers for actual physical systems. Well, often they have some structure to them that yields a controller in some way. So for a mechanical system, for example, it has this nice Lagrangian form that, for example, you could do feedback linearizing control on it. And it depends on the second order form is specific to yielding that controller. Something that's a little more fundamental are linear systems. When we have linear systems, we have a lot of good, like I said, bread and butter for control theorists. Linear systems, there's a lot of theory in designing stabilizing controllers for them. Specifically, we can specify a quadratic cost and do LQR control, which is optimal for linear systems. So it's this idea of structure informing control design that we're sort of latching onto here. It turns out that this linear-like structure can also be identified for nonlinear systems. So if we have f of x plus b of x times u again, let's say we can always factor this. It's fundamental theorem of calculus. We can always factor this as f at 0 plus a of x times x. So it's some constant offset plus all the terms in your Taylor expansion that you can always factor out an x from. And for such systems, okay, well, this looks like a linear system, so we can do, we could solve a Riccati equation at each feedback timestamp for each x we encounter and do LQR-like control for it. And it turns out in practice this has worked pretty well and can do even better than LQR control for nonlinear systems. So a similar factorization exists for aerodynamics for any control affine system. So the idea of being if you write the dynamics of x tilde dot, x tilde is x minus x star, so where you are minus where you want to go. It turns out you can factor in a similar way where you have some matrix function times x tilde plus b of x times u tilde. And you can solve what's called a state-dependent Riccati equation and do feedback in a nonlinear manner using linear-like tools. And it works pretty well in practice. I think there's some analogy with what we talked about before with the certificate-based feedback with contraction theory. So CCM-based or contraction theory-based feedback, as long as you have a decrease condition satisfied, you're guaranteed to be exponentially stable. It's a guarantee. Where this bottom line here is just a decrease condition I've written out for the closed loop system with some controller pi. And without getting, you don't have to sort of know every term in here, but the critical thing is to notice that it depends on state and input samples. It depends on your dynamics, a controller, and a metric. So there's, 3 different things you're learning: dynamics, controller, and some certificate function. It's a lot of things to try and fit to data. In contrast, this Riccati equation-based feedback, it's a heuristic. It's locally optimal. It's no guarantees on stabilizability, but it does work well in practice. And what you're doing is you're only depending on some factors forming the dynamics, and then you're doing Riccati equation-based control. You're not learning a separate certificate function. You're not learning a separate controller. The structure of the dynamics yields your controller design. So what prior work has done is what they've tried to do is let's take this regression loss, let's take this certificate decrease condition, turn it into an auxiliary loss term, and try and fit all these functions to data at the same time. What we propose is try to extract this structure out of the dynamics. Just learn the dynamics and the structure that enables Riccati equation-based control with an auxiliary loss that sort of ensures that these factorizations are valid or consistent. And so what we're learning here is the dynamics and factorizations of the dynamics. So instead, focus on learning the dynamics and some details about them, and do Riccati equation-based control. So in a sense, you're learning less. But the hope is that it still yields an effective controller. So this is precisely what we did. So in simulation, we did this planar quad example where we wanted to track this double loop trajectory. And going from left to right, what we've done is it's an increase in the data set size. So we're going to look at how much data do we need for each different type of method to do well. And on the bottom, I'm going to plot the closed loop trajectory error. So This is a baseline linearization-based LQR. So linearize around your current point, solve a quad equation, and apply that control. Okay, so this is the oracle, so to speak, with the known dynamics. So that's pretty well. Then we did, so this method is basically fit your dynamics to data, just do naive regression, and do linearization-based LQR on that model. And we find it takes a while before it starts to do well. We then tried out the CCM-based, basically the idea of learning dynamics, controller, and certificate. And again, also struggles a bit to get up to the same level of performance. We do our method, it does really well even for a low amount of data. So this is purely learning the dynamics and at the same time learning some structure in the dynamics to enable nonlinear LQR-like control. So we found it's very, it enables very data-efficient learning. And in this plots, we did it for 2 different systems, and along the x-axis is again the data set size, and on the right, on the upper vertical axis is sort of RMS trajectory error, and we've taken sort of multiple random seeds and figured out the distribution in these results, and we get similar case where as you increase the amount of data, you could do better, but our method in green already does really well for low amounts of data, and in fact, for enough data, it beats out the oracle. And the key thing here is to remember that we're learning a controller that's inherently nonlinear, while the oracle is using a linearization-based controller. So remember I said that nonlinear-based control, we hope it does better than linearization-based control, and it does in a lot of cases. So we can find, even now when we're learning the dynamics, we still get that happening. So overall, what we've seen is that enforcing this factorized structure enables a type of control and outperforms as more sample efficient than naive and certificate-based methods. I've got a couple minutes, and I'll sort of, I might have to go a little fast this next section. Forgive me, but we'll move into sort of the final section, which will be more about the adaptive and online setting. So last 2 were about learning a model offline and deploying it online. But like I said, often we're pretty good at deriving at least some basic model by hand. And then maybe what we want to do is sort of fine-tune it online. So here we have a typical feedback loop from state to controller to system, and then you have your feedback arrow going backwards, taking the state back to the input to the controller. For an arm, it could be desired, your state is your position, velocity, your joints. And usually in a controller, like I said, we're relying on some knowledge of the system. And the system model that we're using consists of maybe 2 things, both structure and parameters. Structure could be the fact that force equals mass times acceleration. Parameters are maybe the mass and shape of your payload, that maybe those are uncertain, especially if you're doing pick-and-place operations. Your mass of your end effector and the inertia that you're dealing with are changing. So what adaptive control does is it says, OK, well, maybe we don't know the value of these parameters, but we maintain estimates and try and change them online and learn them online. And what's interesting is that a defining characteristic of adaptive control is that it can guarantee tracking convergence, but parameter convergence is only guaranteed as a secondary result. So parameters don't have to converge, but you'll get tracking convergence. A little odd, but the theory works. So the idea is that this is sort of naturally a form of control-oriented learning, or adapting parameters on a need-to-know basis for control. So the tricky part is maybe we don't know this structure. So maybe for an arm, we can write it. But for a drone in wind conditions, it's hard maybe to derive the interaction with the drone and aerodynamic forces. So the idea is that what we propose to do is learn this model for these forces, and the adaptive part is maybe just the last layer of this deep model that we want to learn. And I think I'm running out of time, but the idea is that if we have data from a drone from multiple different days when we're flying it, or multiple different conditions that we fly it in, we can treat each one as a task, if we use the meta-learning vernacular. And the idea is that the forcing dynamics that we don't know are different for each condition. So the idea of meta learning is learn some shared structure, some shared features for each of these different conditions, and adapt some parameters online that are specific to either task. So this is the concept of meta learning. And what prior work has done is done this with a regression objective, basically differentiating through least squares, or a data fit objective. And we do it instead with a control objective. So we actually simulate the system and then backpropagate through a closed loop simulation instead of just backpropagating through a least squares objective. And I'll skip through, but it turns out, so our method, the baselines are in orange and green, and our method is in blue. So you can see a drastic difference in performance there. I apologize for rushing at the end, but I'll turn it over to questions, I guess, now. So if you have any questions, including in the last part, go for it. Yes.
Yeah.
Sorry.
Very interesting talk. I was just wondering, are you testing on like quadcopters throughout? And is it like dependent on how linear the dynamics of the drone is, the results you're showing here?
Yeah, so it's on a quadruped. Like for this project, it was just the one system. On the previous, the middle project, I don't know which project you mean specifically, just in general?
I'm just seeing always the picture of the drone there. I was just wondering how, like, if you had done it on a helicopter, for example, how well would it transfer,
I think,
do you think?
I mean, the method is pretty agnostic to the system. If you look previously, we did it in two different systems where, so the difference between some of the baselines was not so drastic for this system because it was closer to being linear.
Yeah.
While this one was a lot higher, more highly nonlinear and non-minimum phase. So the delta between our method and baselines
increases with a nonlinearity.
Yes.
Yeah, okay, very cool.
Yeah, awesome talk, Spencer. That was really cool. I was just wondering, I might have missed this, but in the beginning, when you're regressing over models F to learn, is there a certain a priori structure you impose on that class of functions?
The first project, yes.
Yes.
Yeah, so the first one is control affine. F of x plus b of x times u. There's also some, with contraction theory, there are some assumptions about the system that make it simpler to apply these inequality conditions to construct them. One of which is some sparsity in that b of x, which, for example, for mechanical systems, we hope that we can divide our actuated degrees of freedom and our unactuated degrees of freedom, and it comes up with some sparsity in b of x. There's one assumption involving that we make to simplify the construction of these conditions. Okay.
So I guess you have to have some notion of what the actual state of the system is before you begin with this.
Yeah. So discovering a state is not what we do. It would
Okay.
probably be,
Gotcha. All right. Sounds good.
Yeah.
Thank you.
You have a couple from the...
No, I just have my own question. I was wondering, when you learn dynamics and you constrain them to be controllable, do you have any insights on what would happen if the dynamics that you're trying to learn are not actually controllable, or maybe there is some subset of the states that are controllable and some that are uncontrolled? Are there ways to extend your methods to those settings, or what do you think would happen when you try that?
I think you have to find some way of dividing those things out. I mean, in linear systems, like, I'm just spitballing ideas now at this point. In linear systems, you can look at, there's ideas like common decomposition where you can break down the controllable states from the uncontrollable states. So you could look at imposing that kind of structure. I think much like in model order reduction, you'd have to maybe specify how many states are uncontrollable, like much like picking the lower dimension of your model. Nonlinear analogs, I'm not sure about. But that's the approach I would go with, something like that.